Prove that in a parallelogram, the line connecting one vertex to the midpoint of the opposite side trisects the diagonal into 3 equal segments and is itself divided into 3 equal segments at that point. Okay, let us begin. First, let's try to understand the problem graphically. We begin by first considering a parallelogram, and we're going to name its sides very carefully. We are going to consider O to be the origin of some coordinate system, and we have OA. So here we have OA, the vertex opposite to it, we're going to name it as B, and the vertex opposite to the origin will be C. That means we have OACB as the parallelogram. Now, we will also define the position vector of the vertex A and vertex B. So let us suppose that the position vector of vertex A is given by A vector, and the position vector of the vertex B is denoted by the vector B. So here we are going to consider OA vector to be equivalent to A vector and OB vector to be equivalent to B vector. We don't have to worry about C because we can define C in terms of A vector and B vector. All we have to do is join the diagonal, join the points O and C to form the diagonal OC. Now in this parallelogram, we have OA vector. So OA vector corresponds to the vector A vector. Then we have AC vector. Now since OACB is a parallelogram, AC vector is going to be equivalent to OB vector. So here we have AC vector equivalent to OB vector, and since OB vector is B vector, so our vector AC vector is also going to be the vector B. Now what we can do, we can use the triangle law of vector addition. Now in triangle OAC, here we have OA vector added to AC vector, and this is going to give us the vector OC. Now what is OA vector? That's the vector A. AC vector is the vector B. This will be equals to OC vector. Now that means the position vector of the vertex C is going to be A vector plus B vector. Fine. Now this is going to be a vector. Next, we will consider a midpoint on the side OA of this parallelogram and going to name it D. So D is the midpoint of OA, or in other words, we can say that D divides OA into ratio 1:1 internally. So here we'll be applying the internal section formula to find out the position vector of point D. So that means OD vector, this is going to be defined by, so we'll take this one and multiply it with the position vector of A, so that's A vector. Added to, we'll take this one and multiply with the position vector of O, since O it's the origin is going to be denoted by the null vector. So we have A vector plus 0 vector all divided by 1 plus 1. That would be equals to A vector over 2. Anyways, we didn't have to use the internal section formula here because we know that OD vector, clearly OD vector is equals to half of the vector OA. And that's going to give us A vector over 2. However, I wanted to show you how to use the internal section formula because this will be used in a moment. Next, what we'll do, we'll join point B and point D, and this, let's say it intersects OC at the point N. We will suppose that this particular point N divides OC, let's say in the ratio lambda and 1 minus lambda. The reason we're considering lambda and 1 minus lambda, we can assume OC to be of 1 unit. So if we consider OC to be of 1 unit, then if ON is lambda unit, then the remaining portion NC will be 1 minus the lambda. Fine. So here we'll be applying the section formula to obtain the position vector of this particular point N. So we now have, since the point N divides, the point N is dividing OC internally in the ratio, so this time it's dividing it in the ratio lambda is to 1 minus lambda. So here we can apply the internal section formula to get ON vector. So ON vector will be equals to, have to be slightly careful with the diagram. So lambda will get multiplied with the position vector of C. That means lambda times A vector plus B vector. So we have lambda times A vector plus B vector added to, next we have 1 minus lambda. So 1 minus lambda will get multiplied with the position vector of the origin. So we have 1 minus lambda multiplied to the position vector of the origin, which is the null vector, all divided by lambda added to 1 minus lambda. Now this is simply equals to lambda times A vector plus B vector. Or we can say we have lambda times A vector added to lambda times B vector. So this is our vector ON, or we can say the position vector of the point N, which divides OC into ratio lambda is to 1 minus lambda. Now here we can observe that the same point N also divides BD. So let's say it divides BD into ratio mu and 1 minus mu. That means now we can define the position vector of point N in terms of the position vector B and D as we'll take mu. Mu will get multiplied with the position vector of point D. And we have already defined position vector of point D is A vector over 2. So mu times A vector over 2. Added to, we have 1 minus mu. The 1 minus mu gets multiplied with, this is 1 minus mu. Let's get multiplied with the position vector of B. So that's B vector whole divided by mu added to 1 minus mu. This will be simply equals to mu multiplied to A vector over 2 plus 1 minus mu multiplied to B vector. And we can rewrite it as mu over 2 multiplied to A vector plus 1 minus mu whole multiplied to B vector. This is the position vector ON, and let's label this as number 2. Now we can use equation number 1 and equation number 2. So we can compare this, to get lambda equals to mu over 2 and lambda equals to 1 minus mu. Okay, we'll solve this equation to find out the value of lambda as well as mu. So here it's given that lambda equals mu over 2. That implies we have mu over 2 equals to 1 minus mu, which means we have lambda over mu over 2 added to mu equals to 1. So this is going to be 3 mu over 2 equals to 1, which gives us the value of mu as 2/3. So we have mu equals to 2/3. And if we substitute this value back in mu over 2, so lambda is going to correspond to 1 over 3. So that means now coming back to our diagram. So here we have obtained that AON will be equals to 1/3. So 1 minus lambda, this is going to be 2/3. Then mu, we obtain mu to be 2/3, which means that 1 minus mu will correspond to 1/3. Now that's quite evident here that here we have, let's write it down properly. So here what we have obtained that ON, of course ON is going to be lambda times the vector OC vector. And what is lambda? So we have obtained lambda as 1/3 of OC vector. And we also have NC vector. So NC vector is going to be 1 minus lambda times the vector OC vector. And what is 1 minus lambda? That's 2/3. So we have 2/3 of the vector OC vector. So here we have obtained a condition that ON vector equals 1/3 of OC vector and NC vector. So this NC vector equals 2/3 of the O vector OC. And also point O and point C are collinear. Also point O and C are collinear. So this clearly tells us that BD is actually bisecting OC. Hence the line connecting one vertex to the midpoint of the opposite side trisects the diagonal into 3 equal segments and is itself means the line segment BD is divided into 3 equal segments at that point. Hence proved.